Okay, Anna and Kyla, it looks like you're in the chat room now. Are you guys able to hear me? Oh, man. Okay, let's see if this works any better. I'm just going to go ahead, hopefully even if the live stream doesn't go so well, the video will record okay so you guys can still go back and reference that. I'm having to kind of play around with locations where I'm able to stream this and see what the best place is. Real fast, I just wanted to briefly go over last week's homework. The lab that you all did for the minerals, that virtual lab, if anyone had issues, I think everyone who did emailed me. A Word document or Excel is fine. And then you all went through the Mastering Geology and answered the questions on there. If any of you had issues with Mastering Geology, go ahead and let me know. Shoot me an email or a message. But it looks like most people were able to get through it pretty easily. We're going to go ahead with Chapter 2 this week, and this is where we discuss rocks, the actual building block of the solid earth. So, okay. So the focus questions here. Focus question 1 is, what is happening to the rocks in this photo? Typically, I would have asked my live stream viewers about this, but with the lag, I don't think it's possible. So first, we're looking at this picture, and it's taken from a region out west, and you can see that there are some areas of very straight, very, defined structure kind of rock units, And if you look up here, there's a lot of gentle slopes. It looks like a bunch of broken up rocks down here. And then more very upright, straight sections. So we've got areas that are weathering very rapidly. The rocks are breaking down in areas that seem to be pretty resistant to weathering. Focus question 2 is, what is the attitude of the rock layers? So the rock layers, if you look at the banding, they're all very, very horizontal, right? There's little tilt to them at all. And 3, what is unusual about the rock layers? And I'm actually not going to answer that one yet because we will get to that later on in the lecture. Let me just say something to the live chat people real quick. So just like the life cycle of a biological creature or the hydrologic cycle, rocks exist in a cycle also. Rocks are constantly changing and forming and weathering and deforming and reforming. You know, one of the laws of physics is matter cannot be created or destroyed. You know, rocks just go through this continuous life cycle. So the first category of rocks are igneous rocks. And this is where magma or lava cools and solidifies and creates igneous rocks. You can have extrusive igneous rocks, which are rocks that are created as they enter Earth's atmosphere, or you can have intrusive igneous rocks, which are rocks that cool and solidify in the Earth's crust. As these igneous rocks weather, the fragments of them are transported down gradient to a new region where they are then deposited. This is sediment. And as the sediment collects and accumulates over time, it starts to lithify. It undergoes compaction and cementation. And this is how we get sedimentary rocks. So sedimentary rocks are created from sediments or fine grains of igneous or metamorphic. Metamorphism is when a sedimentary rock or an igneous rock, check out that arrow there, undergo deformation either through heat or very high pressure. The important thing to note about metamorphism is that it changes the rock, but it's not a complete restructuring. So it manipulates it and it changes it to a certain extent, but you can still see evidence of the original parent rock there, as opposed to when a rock such as a metamorphic rock or an igneous rock or a sedimentary rock undergoes melting, where it is completely melted down, it exists fully as a liquid, and then it recools and resolidifies into a new igneous rock. Okay, so that's a very brief overview on the rock cycle. Okay, so here we're just looking at the breakdown of the process from the magma to the igneous rocks. So the magma forms when the Earth's crust melts and it extrudes from the upper mantle. And the less dense magma tends to rise towards our surface. And as it rises towards our surface, it can either erupt at the surface as lava, or it can cool within the crust. And when it cools, this is termed crystallization. Igneous rocks are crystallized either from magma within the crust or from lava, which is at the Earth's surface. Most magma never actually reaches the Earth's surface. Okay, the amount of volcanoes that exist is a very low number in relation to how much magma cools near the surface and creates igneous rocks. So the ones that solidify in the crust are intrusive or plutonic igneous rocks. These are only exposed at the surface by uplift or erosion. A really good example of some plutonic igneous rocks are Mount Washington up in New Hampshire, Stone Mountain in Georgia, Mount Rushmore and the Black Hills in South Dakota, and Yosemite National Park. These are all igneous rocks that solidified within the Earth's crust, and over time they were either forced upward through plate tectonics or the weathering of the overlying burden eventually exposed the igneous material. Once these igneous rocks are exposed at the Earth's surface, they immediately start to undergo weathering. Now, igneous rocks are fairly resistant to weathering because of their mineral structure, but they do start to decompose. So as they interact with air and water, the material starts to loosen, it starts to fracture, break up into pieces, or it can actually be dissolved depending on the acidity or composition of the water. This loose material, like I said, is called sediment and is transported down gradient, downstream by gravity, by water. It can be wind transport. Most sediment eventually ends up being transported to the ocean, but can be deposited in other environments. It really depends on the method of transport. You get a lot of sediment that can be deposited on floodplains. You can have wind transport be deposited on open fields. And as they undergo lithification, they are compacted and they are cemented by different kinds of chemicals, and they create sedimentary rocks. Sedimentary rocks and igneous rocks can be deformed by heat and pressure. Typically, the deformation occurs at the formation of a mountain chain. So you can have sedimentary rocks that were deposited, and as you start to get that immense pressure starting to push these units where a mountain building event occurs, they can't just smush together, so they start to bend upward and warp a bit. And that high pressure creates a partial change in the rock. And then eventually, if you get enough pressure or enough overburden, you can actually create enough heat that will start to melt the rock and generate magma, restarting the cycle of creating new igneous rocks. So that was the basic, move from one type of rock to the other. But like you saw in the original image, there are many different paths that a rock can take through its cycle. Okay, so an igneous rock can be reconstituted by magma and be reformed into a new igneous rock. It can just go through that igneous loop. Additionally, igneous rocks can go straight to metamorphism, never go through the sedimentary phase, or metamorphic rocks can be re-metamorphosed into a new rock. Sorry, we're checking on the internet here because apparently it's sucking tonight. Sorry, everyone. Okay. So the rock cycle describes the interactions between the components and processes of the Earth system. Any rock can be transformed into any other rock type under the correct conditions. So not all of you are on campus, but I really want you to start thinking about this. Think about the landscape surrounding your home or your specific campus, your university, and what stage of the rock cycle is happening locally. For instance, in Jamestown, we had a lot of glacial deposits. So those were weathered igneous rocks that were then transported by glacial activity and deposited in the Jamestown area. And they are currently undergoing the weathering and sedimentary process. We've got the Chautauqua Lake, which is getting sediment deposition, and as the sediments accumulate in the base of the lake, they are starting to undergo compaction. We can have some additional erosion from water, high stream activity. There's not a whole lot of metamorphic activity going on. There's no mountain building. There's no overburden accumulating at a rapid rate to create that heat or pressure that would encourage the metamorphic cycle. So I am not going to ask you to diagram the rock cycle. This is left over from my in-person lectures. But this is just a simpler outline of the rock cycle. It's a little less confusing because you don't have all the crazy pictures going on. Just to help you really visualize in a simple way the actual rock cycle. Okay, like I said, rocks are not stable, unchanging masses. They are constantly changing and manipulating and deforming. But this cycle, unlike the biological cycle, which, I think the longest living mammals, like 120 years, something like that. This happens over millions of years and typically in small increments. And the Earth's surface is covered in regions that are all in different stages of the rock cycle. We have igneous material being developed in the Hawaiian Islands and in Japan. We have metamorphic material being created in the Himalayas. We have sedimentary material being created within the, the Canadian Shield and the stable interior of the United States. So you can find different stages of the rock cycle anywhere you go. For instance, Colorado Rockies are eroding, and that material is being carried into the Gulf of Mexico and deposited into the ocean. And like I said, new metamorphic rocks are forming in the Himalayas because there's still that active continental collision between India and the Asian continental plate. Okay, so when we talk about rocks, it's important to understand how we classify and identify rocks. So we're going to start with igneous rocks. Igneous rocks are classified by their texture and their composition. So when we talk about texture, this is the size and shape of the minerals in it, and to a certain extent the arrangement. So the size and shape give us a really good clue as to an igneous rock's origin. Okay, for instance, sorry, my nose really itches today. A coarse-grained igneous rock has minerals that can be seen without a microscope. These are extremely visible to the naked eye. A fine grain requires a microscope to see most of the minerals. Okay, a very fine-grained igneous rock are rocks that solidified very rapidly at the surface or in the upper crust. Okay, this is magma that cooled so quickly that the atoms of different elements didn't have time to really accumulate in significant portions to create these very large minerals. Okay, whereas the coarse grain solidified at depth, so the temperature gradually decreases, allowing these minerals to really build up. Porphyritic means that a rock has two distinct crystal sizes. It has the large grain and it has those very small grains. This indicates that the magma went through two different cooling phases. It went through a rapid cooling phase, it went through a very slow cooling phase, followed by a very rapid cooling phase. So you had that very fine crystal forming, and then all of a sudden the temperature, or you had the very, let's try this again. So you have a slow cooling phase where the large crystals start to develop, and then suddenly something in the external forces changes, and you get a rapid drop in temperature where you start to get that very fine grain accumulating around the larger. Glassy composition is very uncommon. This is typically best seen in obsidian. So what happens is the rock cools so rapidly that the atoms actually freeze in place and they do not get themselves arranged in any sort of crystalline structure. There is no structure in an obsidian rock. Okay, if you broke off a shard of it, it would shatter kind of like glass, and it's actually even sharper than glass. And finally, vesicular, which contain voids left by gas bubbles in lava as it's solidified. Vesicular rocks are they have very low density because they have so many air pockets in them. So you have a vesicular rock that could be about 6 inches across. Your typical rock that's 6 inches across would be probably 3 or 4 pounds, and a vesicular one could be maybe 1 pound, depending on how many air bubbles are in there. So they are filled with tons of voids, which makes them very, very light. They're typically less dense than water. So I was talking about the texture, now let's talk about the composition. The composition is the actual chemical makeup of the minerals or the rocks. Okay, so igneous rocks are mainly composed of silicate minerals. So if you remember from last week, silicate minerals are formed of the silicon oxygen tetrahedrons with the inclusion typically of aluminum, calcium, potassium, magnesium. And this makes up 98% of most magmas. Magma can also include trace elements of manganese, gold, silver, the things we typically mine for ore. So during the crystallization, these elements combine to form two families of igneous rocks. Okay, you have your light silicates, which is called your felsic. These are your feldspars or your silica. They're very high in potassium, sodium, and calcium. So your quartz, your muscovite mica, your feldspars, your potassium feldspar, your plagioclase feldspar, those very white or peach-colored minerals are your felsic igneous minerals. Now you can have your mafic or your dark silicates. These are the ones that are very rich in iron or magnesium, and this is where you get your olivine, your pyroxene, your hornblende, and your biotite forming. Okay, so an igneous rock could form in an environment that would cause more dark silicates or more light silicates. So when you classify your igneous rocks, you typically want to look at the actual composition. So if you look at the image on the right, if you look at the top left right here, this granite, it's kind of hard to see, but this is taken directly from your textbook. It's on page 52. You can see a lot of pink in there with a little bit of black. Okay, so if you remember from last week, that pink is probably your potassium feldspar, probably a little bit of quartz, and your darker minerals are probably your biotite or your amphibole, those really iron-rich minerals. And granite is a very coarse-grained igneous rock. Okay, so if we have a coarse-grained felsic, this is the type of granite we would end up with. The coarse-grained intermediate would give you what's called a diorite. So this one has more pyroxenes and biotites, and it tends to have just a plagioclase feldspar. It won't have any quartz. It won't have any potassium feldspar. So it'll have the plagioclase, which is typically kind of a white appearance, and then those really dark iron-rich minerals. Then you have your mafic, like I mentioned. This is pyroxene. You'll have a little bit of plagioclase feldspar in there, but you'll definitely see amphibole and olivine. And then your ultramafic are the ones that are completely composed of these iron or magnesium-rich minerals. So it's the olivine, the pyroxene, and that's how you get peridot. So you're fine-grained. If you have a coarse-grained composed of quartz and feldspar and biotite, you get granite. If you had an instance where that erupted to the surface and cooled very quickly, you wouldn't get these large grains developing. You would get a rhyolite. It would have just a general kind of pinkish appearance to it. And a porphyritic lift, we talked about two distinct grain sizes. So you would have a granite porphyry. Next to glassy is obsidian. Obsidian is actually a very felsic composition, even though it's typically black or it could have white speckles in it. You almost never see obsidian with a more mafic composition. And then finally, vesicular. You can get your pumice, which is the very light colored vesicular, and your scoria, which is like that burnt red or black colored vesicular. Make sure there's nothing I didn't cover. Oh, another important thing to note is that the mafic igneous rocks or mafic minerals, these are ones that are typically found in the oceanic crust, although they are present on continents. And because they are iron and magnesium rich, they are much more dense than granite or felsic rocks, dominated by the dark colored mineral sweep. And the coarse-grained gabbro formed at depth, and yeah, the basalt is cooled rapidly at our surface. The basalt is a typical composition of basaltic lava flow. Okay, you saw the andesitic. These are the intermediate rocks because there is no, light colored, dark colored, and that's it. Everything on Earth is pretty much a continuum. So the andesitic are between the granitic and the basaltic in composition, so it has a mix of those light and dark colored minerals. This is typically associated with volcanic activity at continental margins because you're getting the mixing and introduction of oceanic crust and the continental crust at these activities. So coarse-grained intrusive is diorite, and a fine-grained is andesite. And then, like I mentioned, the ultramafic is primarily a constituent of the upper mantle, so it's very rare Earth surface, dominated by the darker colored minerals. And then it tends to be, the coarse-grained peridot, and fine-grained is very rare. So, just one thing to think about. So why is the fine-grained rare? Why would we never see that at Earth's surface? Okay, obsidian is that natural volcanic glass. Chemical composition is similar to the lighter colored. And we already covered pumice and scoria. Okay, again, I'm not going to show this because a YouTube video with any YouTube video doesn't work. But tell you what, this time, guys, I'm going to actually copy the link out of the lecture slides and post it in its own link for you all in the class, in the actual notes for this course. So you should be able to find it. Okay, sedimentary rocks. Like I mentioned, these are formed as the products of weathering and erosion of pre-existing rocks. Weathering is a term you'll need to know. It will come up a lot. Weathering is the decay or breakup of a rock at the Earth's surface. There are two types of weathering in earth science. Mechanical weathering, which is the physical breakup of rocks into smaller pieces, so it's actually just breaking apart. Or chemical, which is decomposition. This is where you actually get an alteration in the chemical makeup of a rock into different substances. So for instance, mechanical weathering is when water forces itself through voids until it pushes the rock apart and breaks off pieces, such as on the left. And chemical weathering is what happens to limestone. The calcium carbonate within the limestone reacts with the slight acidity in water and actually starts to dissolve the rock makeup. So this is a good example of how mechanical weathering can actually accelerate the chemical weathering. So if you have a single cube, if you physically break it down into 8 smaller cubes, you now have twice the surface area. So you have twice as much surface area exposed to the slightly acidic water or the wind or any sort of organic material that would have a chemical interaction with it. And if you broke it up again, you'd have even more surface area. So as a rock breaks up physically, it has more surface area for these chemical interactions to occur, which would then accelerate the weathering further. And as these chemical interactions occur, it weakens the rock, which allows for more mechanical weathering. So they're very complementary processes. You very rarely see one without the other, except in extremely arid climates. So some mechanical weathering processes. The first is abrasion. And this is the breakup of rock by forcing water or wind through it. This is the primary mechanical weathering force. It even exists on other planets. You see the image from Mars. There is significant evidence of wind weathering still occurring on Mars. Second is frost wedging. This is what happens when water fills cracks or fractures within a rock and then freezes. I hope you all remember from high school physics that as water freezes, it expands. So the water gets into these cracks, it freezes and expands, and it makes the crack larger. And then if you get a warmer period, that water will then melt, and then it will come back. You'll have water fill back into the hole. Well, now the hole's bigger, and it freezes and expands, and it makes the hole even larger. So you go through this freeze-thaw cycle that actually slowly breaks open this rock as it makes the fractures larger and larger. Sheeting is exfoliation. This is what happens when entire slabs of intrusive igneous rock actually breaks free. I'm going to find you guys a better image of this. I don't think this one explains it very well. So if you have an igneous rock that's forming deep within the earth, you have pressure, equal pressure from the sides and from the top. Okay, but as that top is weathering, you start to have, okay, so here's my igneous rock. You start to have the weathering. So there's not as much pressure above it, so there's not as much material above it, so there's not as much pressure pushing down. Well, all of a sudden you've got these very compacting sides, but nothing pushing it down to keep it contained, so it starts popping up. And as it starts to pop up, it gives this dome shape because it's being constrained on the side, so it's forcing itself upward where there's less pressure. And as it does this, it gives this dome shape. And as it starts to expand in this dome shape, it actually creates what are called joints, which is where it fractures along weaker planes for the expansion. A really good example of this is Half Dome in Yosemite National Park. This is a really good example of the overburden being removed, and it's forced itself up into a dome shape, and then it basically peels off like layers of onions. Okay, if you've ever cut an onion in half and then peels it, that's how it goes. And finally, biologic activity. It can break rocks apart as plant roots grow into it, and as they grow through the cracks and wedges, or the cracks and fractures in a rock, it'll wedge them open. Burrowing animals can also do this. It's also important to note that plants and burrowing animals can also have a chemical weathering impact. Certain plants are highly acidic, and so they can actually start to dissolve rock formations, and animal waste can also do that. So chemical weathering, like I mentioned, alters the internal structure of a mineral. Elements are removed or added, and the original rock is transformed into a new material. So oxygen dissolved in water causes oxidation or rust, and this actually affects iron-rich minerals and rocks. So when you start to get these very bright red rocks, especially out west, you assume this is because of the oxidation of the iron element within these minerals. And then carbon dioxide from the atmosphere actually dissolves into water to form carbonic acid, and this dissolves susceptible rocks. If it has a high enough concentration or occurs over a long enough period of time, you can actually have feldspar minerals that break down into clay minerals, which are much weaker compounds. And silica is carried away by groundwater. Or like I said, the calcium carbonate in limestone actually dissolves in interactions with water. It is important to note that quartz is very resistant to chemical weathering because it is a pure silica oxygen tetrahedron compound. There's very little ability for any sort of chemical weathering to occur interacting with those two elements. So this just shows you the weathering of rocks. So quartz is fairly resistant to chemical weathering. It can undergo physical weathering. The residual product is you just get coarse grains. You get smaller pieces of quartz. Okay. Feldspars will weather into clay minerals. Amphiboles can also weather into clay minerals, but you'll also get iron oxides. And olivine will give you iron oxides. So I mentioned how the sedimentary rocks are then formed. So once these weathered materials are transported and deposited into a new location, they undergo compaction. So this occurs when a sediment layer is buried. And as it's buried, it expels any sort of fluid or water from the sediment pore spaces until there's no void space left, and it's then cemented together. Typically, cementation occurs when mineral-rich fluids precipitate chemicals into the solid spaces. So you can actually have silica precipitate out of the water, calcite, dolomite, clay minerals. These are the common types of cement in sedimentary rocks. Okay, so the compaction and cementation of rock grains form what are called detrital sedimentary rocks. These are how you get your sandstones and shales. These are the solid products of weathering that are cemented together. When you have dissolved material from chemical weathering carried away in water, it can precipitate or settle out of the water to form a solid. These are chemical sedimentary rocks or biological sedimentary rocks. Okay, if they're composed of materials precipitated by organisms such as a shell, they'd be biological. So salt beds from evaporating seawater, like out near the Great Salt Lake, that would be a chemical sedimentary rock, actually. Fossiliferous limestones are limestones that are actually composed of primarily fossil material in a rich calcite cement, and then crystalline limestones. Okay. A few more examples of chemical sedimentary are coquina. These are very loosely cemented shell fragments. It looks like it's a whole bunch of tiny pieces of shells that are just clinging onto each other for dear life. There's no really clear visible cement. It is just all shells. Chalk is actually composed of hard parts of microscopic organisms. Travertine is an inorganic limestone that forms in caves. Chert, flint, jasper, and agate are actually microcrystalline quartz. Salt and gypsum form and evaporate deposits, and coal is actually a product of mostly organic matter. Okay, so this is, again, a table from your book. So this looks at the detrital sedimentary rocks. So like I said, they are identified based on their texture, okay, so the grain size, and to a lesser extent their composition. Composition really doesn't come into play for the most part in detrital sedimentary rocks. It is primarily focused on grain size. So the coarsest grain size sedimentary rocks are conglomerates or breccia. So the really big difference between a conglomerate or breccia is that breccia have particles within it that are very angular in shape. You know, we're talking, you know, it looks like a pointy rock that was just broken off with a hammer. Conglomerates tend to be very rounded particles, typically through a lot of water weathering processes that have really just smoothed them out and created a nice soft round edge to them. Medium grain size give you sand or sandstones. So these are still grains that are visible to the naked eye, but they are all uniform in size and not very coarse. Next is silt. A siltstone, you will not see the grains unless you're using a hand lens or a microscope. Some geologists actually, if they're trying to differentiate between a siltstone or a shale or mudstone, which is below it, they'll actually break up a tiny piece of rock and rub it on their teeth, and if you feel a little bit of grit, it's a siltstone. A mudstone or a shale should feel smooth if you break it off and rub it on your teeth. Geologists have really bad teeth, guys. They are like destroyed. Okay, so this focus question says, what is a detrital sedimentary rock called that has an average grain size of 1.5 millimeter and has very little feldspar? So 1.5 millimeter would be a medium or a sand, okay? And an arkose, I didn't mention that earlier, an arkose is very high feldspar content, okay? So something that has very little feldspar would be a sandstone. Oops, there we go. Okay, this table is also in your book. These are chemical and biochemical sedimentary rocks. So these are identified first based on their composition and then their texture. So it's you know, the opposite of the detritals. Typically, you want to use your mineral property test to kind of determine the chief mineral makeup of these rocks. So your focus question here is, which chemical sedimentary rock is rich in the mineral calcite, has a microcrystalline texture, and lacks fossils? Okay, so if we have a mineral that has calcite, or if we have a rock that is rich in the mineral calcite, it's going to be a limestone or a dolomite. So here we have all of our calcite-rich rocks. We have our fine to coarse crystalline, we have our microcrystalline, and then these are clastic, so they actually have visible items. So here we have a clastic with shells and clastic with very visible shells. So we're looking at a microcrystalline limestone here. It has no fossils present, microcrystalline texture, and it's rich in calcite. Okay. Coquina, like I said, is made up of a ton of shell fragments and is typically cemented with calcium carbonate. Fossiliferous limestone, various shell sizes, but there is more cement or the calcite for composition than fossils. And then you get your chalk, which is the microscopic shells and clay. It's important to note that these last three are biochemical limestones. They're all a byproduct of fossil or biological activity. Your crystalline limestone, your microcrystalline, and your travertine are all, these are all mineral-based. They're non-organic. You can also get chert, which is quartz and silica in composition, very fine crystalline. Your rock gypsum, your rock salt, which is halite, and then your bituminous coal, so your organic matter byproduct. Interpreting sedimentary rocks can give us a very good clue as to the environment they formed in. So internal and external structures, features, and composition give us really good ideas. So for instance, this first picture, it's talking about ripple marks here. Well, if you're getting ripple marks, we're looking in a flowing water system. It's possible it could have been a lake, but it's more likely it was a stream to cause these continuous ripples. If you get cross-bedding, this is actually indicative of the water flow changing direction over time. So you've got water flowing this way, and then at some point it changes and goes that way. So it gives us a really good idea of how water movement has evolved over time in that region. You have feeding burrows of biological activity, and your fossil assemblages actually give us a really good clue as to the biological activity and organisms that existed when this rock was forming. Again, YouTube video, I'll post a link for you guys. Metamorphic rocks. So metamorphosis means to change form, and most people understand that concept of, butterflies, a caterpillar metamorphoses into a butterfly, but it actually applies to rocks too. So these are rocks that form from changes to pre-existing rocks of any type. The changes are textural and compositional, and what happens is the parent rock is introduced to an environment of higher pressure or higher temperature, causing these changes. Metamorphism is broken into two groups, a low grade or a high grade, but a complete remelting of parent rock never occurs. So here we're looking at metamorphic rocks. So we have our parent rock shale, like we just talked about in our sedimentary. Okay, that's a very, very fine-grained, almost impossible to discern a grain at all sedimentary rock. If it undergoes a low-grade metamorphism, it has low temperature and low pressure. And what happens is it takes these loosely packed, slightly misaligned clay minerals and aligns them into a very structured formation, very tightly packed, to create slate. So slate is much harder than shale, more weathering resistant. Slate is what chalkboards used to be made out of. Here we have a granodiorite. So we talked about in the igneous, you have the granite, and then the intermediate would be a diorite. So what happened here is this is kind of just forming really on that border between the two. So it's best classified as a granodiorite. You have a randomly oriented mineral grain. These minerals just kind of grew or developed in whatever arrangement they felt like during the cooling process. So high-grade metamorphism is when it undergoes a very strong compressional force or very high pressures and or temperatures. As that happens, what occurs is that similar grains migrate toward, or similar minerals migrate towards each other, and everything is forced into alignment, giving you these very defined light and dark banding. Okay, so the very high temperature gives you this linear occurrence, and then the high pressure actually creates this deformation, giving you these waves or these folds within the rock. Most metamorphism occurs in one of two settings. You can either get contact or thermal metamorphism. This is where the temperature increases because magma is actually starting to intrude into your rock unit, or regional metamorphism. This is where the pressure and high temperature occur. Sorry guys, it's been a long day. This is where the pressure and temperature occur because of mountain building activities such as continental collisions. So metamorphic rocks are found in the exposed cores of mountain ranges and in exposed crystalline basement rocks. So the Adirondacks are a really good example of metamorphic rocks, and large areas of the Canadian Shield, or the really stable Canadian interior, are good examples of metamorphic rocks. When we talk about basement crystalline rocks, these are the rocks that make up the continental crust beneath layers of sedimentary rock. So you'll have the overburden of sedimentary rock, and as those are weathered away, it will start to expose the crystalline rock that basically underlies everything on the continent. Similar to igneous rocks, metamorphic are identified by their texture and composition. Okay, because metamorphism can change the texture of a rock, this gives us a really good indicator as to the type of metamorphism occurring. So low-grade metamorphism just makes rocks compact and more dense. They're just much denser than their parent material. But high-grade can actually cause crystals to recrystallize and accelerate the growth of visible crystals. Metamorphic rocks can be foliated or non-foliated. Okay, foliation is what we're looking at here. So it's where flat and parallel alignment of minerals occur in layers as a result of the metamorphism. Okay, so this includes the parallel alignment of micas. You can actually get, in sedimentary rock, parallel alignment of pebbles. They'll actually force all your pebbles to line up in a nice linear fashion. Separation of light and dark minerals into bands, and the development of rock cleavage, which is very similar to the mineral cleavage we talked about last week. Common foliated mineral or metamorphic rocks. Slate has one direction of rock cleavage, so it's very much like the biotite or mica. It just shears off in sheets. Slate is typically from metamorphosed shale or volcanic ash. Phyllite has larger grains than slate, and it gives it a bit of a glassy sheen, and it also causes it to have a more wavy appearance because it's not as uniformly composed. Schist is formed by regional metamorphism of shale, but because of the higher pressure and temperature, it has larger mineral grains than the phyllite. It can have a glossy sheen, but it's not as distinct as the phyllite. And finally, gneiss is identified by the fact that it is banded. It has that light and dark banding. Like the defining factor of gneiss is light and dark banding. It can also have intricate folding going on, but that is not necessary for it to be classified as a gneiss. You can also get non-foliated metamorphic rocks. This is when the deformation of the parent rock is from stable minerals. So like we talked about, quartz is a very stable mineral, undergoes very little weathering. If it undergoes a higher temperature and pressure, it becomes more compact and more dense, creating quartzite. So the parent rock is typically a quartz-rich sandstone, and like I said last week, quartz can come in a variety of colors. So your quartzite can actually be a variety of colors too. You can have pink and green and purple, brown. Marble is a coarse crystalline rock dominated by calcite. The parent rock is typically limestone. And again, marble can occur in a variety of colors. It's typically on a scale of dark gray all the way down to a pure white, with a lot of variation in between. Okay, so here this is what is the name of the foliated metamorphic rock known for its distinctive mineral banding. So we have, the only one with very distinctive mineral banding would be right here, okay? And like I said, that's a gneiss, typically coarse grained. Parent rock is shale, granite, or volcanic rocks. So this just gives you a really good reference point of what characteristics to look for in a metamorphic rock. You guys are going to do it because you have a virtual lab, but in my physical lab, in my lectures, my in-person classes, people really struggle with marble and the quartzite because they can look very, very similar. They're both based off sedimentary rocks. No sort of definable texture or banding. Marble forms from limestone, typically. Limestone is composed of primarily calcium carbonate. If you remember from the mineral section, I said calcite actually effervesces or fizzes if you put hydrochloric acid on it. Marble will also fizz if you put hydrochloric acid on it. If you have marble you want to test it on, go ahead. Don't do it on a statue in a museum. They will probably kick you out. But that's a really easy way to kind of differentiate between marble and quartzite. And then your metamorphic video, again, I'll post the link online. And a geology joke, because these are the best. So this is the understandably less popular geology version of rock, paper, scissors, known as rock, 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 because igneous erodes the sedimentary, and metamorphic alters sedimentary, but igneous melts metamorphic. It's hilarious. So sorry about the issues with the video this week. We're having some internet problems, and I was hoping we got it solved in time, but it looks like we didn't. Class this week, and I'll send out an email, you're going to do a virtual rock lab, very similar to your virtual mineral lab. If you're having problems with the little answer table, type it into an Excel file or a Word file and submit it that way. That is also acceptable. Don't worry about that. It's not a big deal if it's not in that table form. If you're having problems where it won't let you check the mineral or check the rocks to verify your answers, shoot me an email, let me know. I know one person had issues with the mineral lab, but most people shouldn't have problems with that. You have your Mastering Geology questions to answer this week. I think you have some virtual field trips on that, which are super cool. And then you have your discussion for this week. So make sure you take care of all three of those. Again, if anyone has any questions for me, shoot me an email. I try to respond to those fairly promptly, or post on the question board for your classmates. If you have questions about rocks in general, feel free to post it on the question board. And I think that's it. I'll be back next week. I will be in a place with better internet, so hopefully it'll work better, and I will see you all then. As soon as I figure out how to